Yeah, let's start off everyone. Chalo, cams on everyone. Great. So this was the last thing that we did based on IAR. So go ahead. This is the top view. We have a conducting ring. So on this conducting ring, we have a rod. This is hinged in the center. Rod of mass m and take the length to be r. There's a magnetic field in the region B. And we have a resistor connected to the circuit like this. This is resistance R. Take the length to be L. So if you look at this from the side view, the picture would look like this. So we have a rod here. The rod is sliding about the center. Able to visualize how it is? Now someone kicked this rod with omega naught. So here the resistor is like this. Someone pushed this rod with an angular velocity omega naught in presence of a magnetic field. So there is a magnetic field in the region which is into the plane. Hope the picture is clear, everyone. So this rod actually slides horizontally on it. It's like your fan. Your fan ka blades are there. Think of that one blade as a rod and that is sliding on this ring. So initially, the rod has no resistance. And initial angular velocity of the rod is omega. Find omega of the rod as function of time t. So something happens. This rod actually starts slowing down. You can neglect any gravity. It doesn't matter. First, figure out why is the rod slowing down. Hope the picture was clear. Someone is confused with the picture, please ask me. Hope everyone figured out the story. If a rod rotates, it will produce EMF. If it produces EMF, there is a resistor, so there will be a current. If a current is passing through a rod, you have a current carrying rod in presence of a magnetic field. That means there will be a magnetic force. That force will drag the rod back. Try. Yeah, I'll give you a minute more. Let's see. So let's say after time t, this thing has a velocity omega. Then how will it act like a battery? Put plus q charge, it will go to the left hand side. So this will act like a battery like this, where EMF is b omega L square by 2, because of which you get a current I. Current will be E by R. So now you got a rod in presence of a magnetic field. This is your hinge. And the current I is flowing this way. Take a small cross section dx at a distance x. On this small cross section, the force will be df downward. So omega will be this way, but alpha will be this way. Omega and alpha are in the opposite direction. The force on that small rod will be current I, length I dxb. So the torque on that small rod d tau will be the perpendicular distance into force. Therefore, the torque on the rod will be integral I b x dx. This will go from 0 to L. The torque acting on the rod will be I b L square by 2. This is the torque acting on the rod. This is nothing but, I is nothing but how much? I is b omega L square by 2R. So torque on the rod is nothing but I alpha. This would be b square omega L power 4 by 4R. I of a rod is nothing but ml square by 3. Alpha is minus d omega by dt, minus because it is decelerating, is b square omega L power 4 by 4R. So d omega by omega will be minus b square, when L square goes off. You'll get 3 here, and then you get 4 mr dt. Limits will go from omega not to omega and 0 to t. There. Right, Vihan, you almost got there. If I ask you a question, find the total heat produced, how will you find that? If you want total heat, this is nothing but integral I square R dt 0 to infinity. There is a much better way. This is nothing but half I hinge omega square, isn't it? The total kinetic energy of the rod becomes heat. Eventually the rod will stop. So where did all this kinetic energy go? It has become heat in the resistor. All clear with this? There you can get questions based on this, on rotation based. Any doubts on this? Next thing. So that's a little bit on the motional EMF part. So when the rods are rotating and everything, the next thing is induced electric field. Because still there is one part of the story which was still confused. Faraday's law says when there is a change in flux, there is an EMF. Fair enough. And we saw whenever these conductors are moving in a magnetic field, we got motional EMF that we proved. We said there is a magnetic force because of which there are electrons and blah 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 and everything we proved it. The problem is this: if you take a coil and if you have a magnetic field B naught T, there is an EMF there. There is no motion, nothing. So if you just have a magnetic field which changes with time, that will still create an EMF. So we have a problem here. What is the issue? So if you have a time varying magnetic field, this will create a change in flux, and because of that you get EMF, and that's what we saw in Faraday's law. All great. Problem, we got an EMF here which is nothing but electric potential. So the issue is, how can magnetic field create electric potential, isn't it? You have a magnetic field and you're getting an EMF. EMF is nothing but electric potential. So if you're getting an electric potential, this must be due to electric field. Because magnetic fields cannot create electric potential. Only electric fields will create electric potential. And this magnetic field cannot create electric potential. That means somewhere in the middle of the story, right, something is missing. There is an electric field somewhere. There's no other way to explain this. So in the story, something is happening in the middle. So there is still more somewhere in the middle. Something happened in the middle. We are not sure what is happening, but there must be an electric field somewhere in the middle. So that means an electric field must be created somewhere. Great. So that means a time varying magnetic field somehow creates an electric field. So we are not interested how it creates, but we are interested in how much it is creating. Now, for our study of 11th and 12th, we will keep it very simple. We will take pretty symmetrical shapes. We will not do any weird ones. So we will study only for cylindrical magnetic field regions. That is how much our portion is limited to. We study these induced electric fields due to cylindrical magnetic field regions. Meaning, so the field is coming out of a cylinder. Basically, these are the kind of fields which are created by solenoids. These things have a pretty good symmetry. Any other shape, it becomes very difficult to figure it out. Solenoids generate these kind of fields. Great. So let's start with this thing. So consider a cylindrical region of radius r. Let's say this is the top view. Let's say at a distance r, we are trying to find the electric field. Let this be B naught t, B of t. So B is changing with time. We don't know the function though. So same thing, if you look at the side view would look like this. Now the thing is, we don't know how is this electric field. So when you don't know in 3-dimensional, you can divide anything in 3 perpendicular directions. So I will say, let's say the field can be in this direction E1, the field can be in this direction E2, the field can be in this direction E3. Since we don't know exactly how the field direction is, let it be in 3 perpendicular directions. So tangential direction, radial direction, and vertical direction. So resultant of these 3 will give you the field. So if you can find E1, E2, E3, my job's done. I got the electric field. Let electric field have 3 components. In 2-dimensional, you need 2 perpendicular directions. In 3D, you need 3 directions. E1 is the radial direction away from the axis. E2 is parallel to axis. And E3 is tangential direction. Great. Now, from Faraday's law, we also know the EMF in the loop will be minus d phi by dt, where flux is nothing but area into dV by dt. Great. Now let's try to figure out this E1, E2, E3. Let's try to find E1. So in this cylinder, consider a Gaussian surface. So if E1 exists, so E1 will be radial direction. Right? So E1 is all radial direction. So the electric flux will be E1 into surface area, 2 pi RL. Let the radius be R and let the length be L. But we know from Gauss law, electric flux is nothing but Q enclosed by epsilon. Do we see any charges here? All we have is only a time varying magnetic field. We don't have any charges. Since Q is 0, E1 has to be 0. There, we proved you cannot have a radial field in this kind of scenario. Because if there's a radial field, there will be a electric flux and there should be a charges enclosed. So E1 is gone. Next thing. When you take this infinity thing, remember this is an infinite cylinder. Now for infinity special, remember every point is a midpoint. Because no matter where you stand, it looks infinity on all the sides. That means if you consider these rings, right, all these points are All these rings are identical. Since every point is a midpoint, due to infinite length. If all are identical, that means all have same potential. Therefore, all the rings are equipotential. And if it is equipotential, that means the field must be 0. Why? In the direction of field, potential changes. And now you are saying along the axis, the potential is same. So the field along the axis cannot exist. Clear with this? Therefore, E1 is 0, E2 is 0. The only guy left is tangential. And that kind of makes sense. The EMF in a loop, right? If you take a circle, we get EMF in a loop. So field also must be in a loop. But just to be sure, we are being careful that E1 and E2 don't exist. Any doubts on these two logics here? Why E1 is 0 and E2 is 0? So the only one left is E3. Therefore, when we get the EMF in the loop from Faraday's law, which is minus d phi by dt, and we also know from electrostatics, EMF is nothing but integral E dot dl. This E here will be E tangential because E1 and E2 are 0. That is the reason we took a cylindrical shape. You can prove that the only E tangential exists. So there, this is your final formula there. So whenever you want to find an electric field, this is a tangential field. D tangential dot dl bar is given by d phi by dt. This is your magnetic flux, huh? Be careful. The rate of change of magnetic flux. And what about the direction? The direction is given by Lenz's law. Just like the current ka direction. If they ask you to find the direction of electric field, assume there is a loop, find the direction of the current, that will be the direction of the field. Let me show an example. So if you take a cylindrical region, right, you can say that E will be constant because it is a cylinder. E comes out of the integral. So it becomes easy to solve. That is the whole story. If you saw in Gauss law, Ampere's law, every time, right, we want that thing to come out of the integral or else you can't solve. So listen to this example. So let's say we have a cylindrical region. Top view. There is a magnetic field here. B is equal to B naught T. Up to radius R. So consider a small ring of radius R. Step 1, find the flux. B naught T into pi R square. Step 2, write that thing. Integral E dot dl is equal to d phi by dt. It's easy to remember. Huh? There is no need to do all that I did. Remember, EMF from Faraday's law is d phi by dt. From electrostatics, when it is integral E dot dl. There, you can just equate them. That's the easiest way to remember. Now, since it is uniform, here if you see at every instant, E is parallel to dl. This will be E bar and that will also be dl bar. So this will become E dl cos 0. d phi by dt will be b naught pi r square. that E comes out of the integral, and integral dl will be 2 pi r. B naught by r square. Therefore, the field inside will be B naught r by 2. For r greater than r, means now you're taking a ring outside, but the magnetic field is only present up to capital R. B naught t into pi capital R square. Same story, integral E dot dl is equal to d phi by dt. LHS will be E into 2 pi small r, the distance of the thing. This will be B naught by r square. So here you'll get E naught is equal to B naught r square by 2 small r. You can clearly see this is proportional to 1 by r and this is proportional to r. Again, remember, this is only for B naught t. If you give a different function, it will be something else. So if you try to plot the graph of E versus R graph, it's a linear function, it increases, then it decreases. And how will the field lines look like? The field lines will be concentric circles. You have never seen electric field like this. You have seen magnetic field like this. We have never seen an electric field of this sort. You cannot create these things with charges. And what is the direction? Lenz's law. Flux is increasing, so my B induced will oppose, should be upward. So the direction is anti-clockwise. So all these field lines will be going anti-clockwise. That is your field direction. Circular field lines. Other steps clear, everyone?
Sir.
Hmm.
So in this, we're taking a region of space, right? So it's not like it needs a wire for there to be that EMF. Sorry, electric field.
Right. Right.
So it'll happen both ways, both times.
Meaning? What are
Means
you
it doesn't
talking?
matter wire is there or not, it will still
It's
create the
not there,
electric
na?
field.
Yeah.
Okay, so I thought
Wire has nothing. Wire has nothing to do with electric field. Later on, you're going to see that electric field will. If you have a wire, then you get EMF.
got it, sir.
It's like you tied a balloon here, and you saw balloon is drifting this way. So wind is blowing which way? To the right.
Yes,
If I remove the balloon, wind is blowing which way?
right.
The wind doesn't care about the balloon. So EMF is the result because of this electric field. All clear with this? Now I'll give you a system. Now you guys try to get the values. So let's say here field is into the plane, and here field is out of the plane. This is radius r. This is radius 2r. Top view. This is how the magnetic field is. It is B naught T minus K cap for r less than r. Then the field is B naught T plus K cap. So direction has changed for r between 2r and r. Then it is 0 for r greater than 2r. Plot electric field versus r graph. Again, remember the story is the same. Find the flux. First choose the regions. Here, how many regions are there? There are 3 regions. Up to r, between r and 2r, and outside. They have to do it 3 times. Find the flux, differentiate, equate it to integral E into 2 pi r and get the. Try. You got 3 minutes. See the first part. First part was easy. So consider a surface between 0 to capital R. Flux will be B naught T pi R square. I'll take the downward as positive for now. Doesn't matter, the directions we'll see. Then integral E dot dl. d phi by dt. This will be E into 2 pi R. This will be B naught pi. This is small r square. So we got E naught B naught R by 2. And what about the direction? Flux is increasing, so B induced will oppose. So direction is anti-clockwise. So this field length will be anti-clockwise. Clear? That was easy. What about the second part? For the second part, if you take somewhere here, for R between 2R to R, the flux will be, I'm taking downward flux as positive, B naught pi R square minus P naught T. Because the field has changed direction, you have to subtract the flux, which will be pi small r square minus pi capital R square. Isn't it? From small r, from capital R to small r, the field is upward. From 0 to R, it is downward. So the fluxes will subtract. This thing comes out to be B naught T pi 2R square minus small r square. Integral E dot dl is d phi by dt. E into 2 pi r is equal to B naught pi 2R square minus R square. So we get the field will be B naught by 2R square minus R minus R. This is not a parabola or anything. Now, if you do dE by dr equal to 0, you will notice you'll get R is equal to R root 2. Meaning at this point, you're getting a maximum value. Then, if you also notice something here, you will need this for the graph purpose. B naught by 2, that will become minus 2R square by small r square minus 1. Look at this. The slope is negative. And if small r increases and decreasing in magnitude. That means this thing, ka direction will change after r root 2. And this whole graph will just keep on decreasing only, but it is decreasing at a slower rate. We will see that also, how the graph will look. And for the third part, for r greater than 2r, the flux will be B naught T pi r square. B naught T 4 pi r square minus pi r square. This will be B naught T minus this would be there. So this is the magnitude. So if you try to plot this graph, Initially, it is a linear function. Increases till r. From r to 2r, I said it is a curve. It's not a straight line, that much I know. It is decreasing. So there are two possibilities, right? It could be like this. But here, look at the problem. The slope is becoming more and more steep. So this is not possible. It should have been something like this. It's a decreasing curve. This point will be r root 2. That is the point where the field will 0. Then it will still continue to decrease, but the direction is reversed. This will go till 2r. And after that point, it will decrease as 1 by r function. Minus indicates the direction is reversed. So if I try to draw the field lines, they will look like this. So you'll have initially anti-clockwise. This is your anti-clockwise field. And at r root 2, the direction will reverse. This is a clockwise field. So it will be still concentric circles, but the field direction will change. Direction of E bar reverses at r root 2. Wait, I think I did some mistake. D by dr is 0, na? That should be maxima actually. If I substitute r here, what am I getting? I'll get the previous value. If I put r root 2, what do I get? That is maxima, na? This thing should decrease. Why am I getting a maxima there? So it is taking a turn somewhere. Is this positive or a negative value? Yeah, that is root 2r minus, that's coming 0 only. I think that graph na, should have been, if you actually try to plot the graph, it would have been like this. Isn't it? Look at that function now. I'm getting r root 2, right? That is actually a minima. If I double differentiate this again, if I substitute r root 2 here, I'm getting 0. Or did I goof up something here? I did a mistake. Sorry. dE by dr is not 0. At r is equal to r root 2, E is 0. The graph is right only. I did a mistake. Clear with this? That's not differential that I wrote wrong. When you keep r is equal to r root 2, I'm getting E is 0. The dE by dr is only for the slope ka purpose. I want to just check whether it is slope is negative or positive. Is the graph clear, everyone? You can just mess up few things and things can become pretty messed up. If I can put 3b naught here, the answers will change. So this is how you do. Any doubts on this? Let's see one more. Process is clear, no? Find the flux, put it in this formula. You'll get the answer, get the direction from Lenz's law. That is the story every time. Top view, let's say we have a magnetic field region. Where B is equal to B naught T square. So from the center, you kept a rod. This is hinged. Light rod. At the end of the rod, you attach the charge plus Q. The rod of length L is hinged at one end. And the other end has a charge Q and mass M. System is released from rest. The magnetic field is B naught T square. So something happens. This rod starts moving. Find tension in the rod at time T. So figure out why the rod is moving. Once you figure it out, then draw an FBD and then get all the forces and get it. Did you guys figure out why it is moving? A time varying magnetic field will create an electric field. That electric field is dragging the charge. So it starts going in a circle. If you go in a circle, you'll get a centrifugal force. Flux will be V naught T square pi L square. So your field is also not constant. Field is also changing with time. F electric will be QE. Therefore, acceleration will be Q V naught L T by M. Integrate this, you'll get velocity is equal to Q B naught L by 2M T square. So you have to integrate. A is not constant. So what are the forces on this particle? The electric force is acting this way, that is EQ. Okay, that won't create any tension. Velocity is V this way, magnetic field is B into the plane. We have tension towards the rod, we have centrifugal force. Most common mistake, people forget the magnetic force. There is also a magnetic force. If you have velocity in presence of a magnetic field, you'll have this. There is one more problem here. We are going to ignore this. If you have a time varying electric field, that actually creates another magnetic field. We are ignoring it. This is the problem with electric and magnetic fields. If something changes with time, that will create something else which that changes with time, and it just keeps going on. There, you're done. So tension plus F magnetic is QVB is equal to mv square by L. You know everything. You know velocity, you know B, yeah, you know everything. If you do this, you'll actually get tension is negative. That means the rod is not pulling, rod is pushing. Magnetic force dominates here. Clear with this. So a time varying magnetic field creates an electric field, and that starts accelerating your charge, and you go in a circle, they get a centrifugal force. But now, because you gained a velocity, the magnetic force comes into the picture. Electric field is only there to increase your speed continuously. Any doubts on the steps? Clear, na, Shashwat? Niharika? Devansh? Clear, na, Niharika? Arush? Adi? Let's see one more. So how will they ask a question in advance? So we got a charger disk. Charge Q, mass M, radius R, neglect gravity. So this disk is literally floating. This is a charge disk at rest. Then what you did, you went and switched on the magnetic field. So initially there's no magnetic field, suddenly there's a magnetic field. Magnetic field B is switched on instantaneously. Or switched on suddenly. Something happens and the disk starts rotating. Find angular velocity of the disk. So that's the first part. First, figure out why the hell it is moving, and then try to find out what is it. Initially, the disk is just floating in space. The moment you switch on the magnetic field, again, B is constant. Initially, it was 0. Now it is suddenly B. In that small time span, something happened and the disk started rotating. How do you find angular velocity of the disk? Anyone confused with the picture? Anything that you're not clear? Did you guys get the story? Right. So I told you this multiple times. There are certain words that suddenly you hear that word, you should, immediately the bulb should glow. Was this an impulse problem? So initially magnetic field was 0. Finally it is B, but the time is very small. In a very small time, you change the magnetic field. So there'll be a huge electric field for a small time. So the dispel thing, someone kicked it. So if there's a time varying magnetic, now unfortunately I don't know what is the change in field. I know the change in field, but I don't know the time. How do you proceed from there? Think. I'll give another minute or two. In case of rods and particles, impulse problems, it is impulse is change in momentum. But this you're saying it is rotating, so it should be an angular impulse, isn't it? So angular impulse is torque into time. So can you somehow get torque in terms of B? Think. I'll give a minute or two. Give it a try. I'll just get some water and come. Let's see. So how do we proceed? First thing, the same story, integral E dot dl is d phi by dt. This will be E into 2 pi r. The rate of change of flux will be d by dt into b into pi r square. This will be r by 2 dv by dt. So the thing is, I don't know how b is changing. This is your electric field as function of r, and we have no idea how b changes. Now, if you take this disk, at a distance x from here, consider a thin ring. Of thickness dx. So on this thin ring, we have an electric field E bar, which is tangential. Again, this electric field act only for that small time dt, but the value is pretty large. So B changes from 0 to t in very small time t. Now, the torque on the ring will be tangential force into radius. So torque on the ring, the tangential force will be E into the charge on the ring. Charge on the ring is nothing but Q by pi r square, total charge by total area, into 2 pi r dr. So this will give the total torque on the disk will be pi and pi will go off, 2 EQR square integral r square dr. Am I missing something? That E is also there, no? That E is r by 2 dp by dt. That is your E. Q of the ring is Q by pi r square 2 pi r dr into r. So torque on the disk will be, remember dB by dt is constant. You're integrating with terms of r. So dB by dt, 2 pi goes off. We'll have q by r square integral r cube dr. That would be qr square by 4 dB by dt. And we know torque into dt qr square by 4 integral dB. Torque dt is nothing but change in angular momentum. Now you're integrating with time. And this will be qr square by 4. This will go from 0 to b. So the first integral is with respect to position, second integral is with respect to time. So when you're integrating with position, time won't matter. This will be I of the disk into omega. I of the disk is mr square by 2. R square will cancel, M2 will be there. So this will be QB by 2M. Check, that's your answer. Right here. Clear with the steps, everyone. Extensive, matlab, you can see how it is. In that small time dt, you get an electric field for that small time dt. So each ring will have different electric fields because R is changing. So you have to first calculate the torque on each ring and then integrate for the full disk. And then that total torque on the disk into time will give you change in angular momentum of the disk, which is I omega. Clear with this? Any doubts? Any step that you're not clear? This is another good one. We'll have a break. We'll continue this after the break. Come back by 9:30. Take a 5-minute break.
सर
हाँ देवांश,
सर एक डाउट है क्वेश्चन 19.
क्या हुआ?
सर यहाँ पे तो आपने क्यू डाला ना, मतलब तो फिर ई रेडियल 0 क्यों है?
क्या?
तो आपने क्यू इंट्रोड्यूस किया सिस्टम में तो ई रेडियल 0 क्यों गया?
ई किसका ले रहे हो बॉस? ई किसका है? ई रेडियल फॉर हु इज क्रिएटिंग दैट ई रेडियल? बोलो ना, who is creating the E radial? Can magnetic field create E radial? तो उसके बाद तो Let's start off. Let's try this. Devansh, did you figure it out? You are only saying E radial, E radial. Simple question पूछो. Who is giving that E radial?
सर आपने जो लास्ट पेज पे डेरिवेशन किया था उसमें तो आपने बताया था ना Q इनक्लोज 0 है तो नहीं होगा ये.
So you are saying so अगर मैंने चार्ज निकाल दिया, then you agree there is no E radial. So that means you are saying E radial is coming because of this charge. So you are saying the charge will have the force on itself because of its own field. So मुझे ये बात बताओ. Let's say I kept a charge Q in space. Find the force on the charge. कितना था? E into Q. What is E? KQ by R square. इस खुद का चार्ज का फील्ड खुद को मूव करेगा. That's what you're saying. Convinced? Happy? क्वेश्चन में पूछा था FBD ड्रॉ किया था. You are taking the field due to the charge and putting it on the same charge and you're finding the force. How do we approach this? This is a pretty good one, right? This is how advanced questions will be. Think. Take 2 minutes. Think about it. Let's see if we can figure out few parts. I have question though, I hope you understood. So the ring is initially given velocity V0 without any angular velocity. Once it enters, it started pure rolling. So if I had to help you with a picture, after entering, velocity becomes V and omega. Can you start with V and omega? Let's find V and omega. Then see if you can get any ideas. Because problem ye hai, this is not a cylindrical magnetic field region. So you can't use any standard formulas that are derived. So we need to approach this in a different way. What is work done by magnetic force? 0. There is no other force, so energy must be conserved. Start from there. So half mv square is half mv square plus half I omega square. Since it is not slipping, V is equal to R omega. And it is a ring. So V is equal to V0 by root 2. Omega is V0 by root 2R. This much you can figure it out. That means one thing is clear. Velocity of center mass is not constant. First option is wrong. If velocity is changing, acceleration is gone. You can eliminate 2 options. You're stuck with B and C. Answer is B. That is given, but how do we figure it out? Think. Take a minute more, then I'll show you. Again, these are the kind of questions, the previous one and this one, these things you should have seen few models. So something like this comes, you will be able to attack. So when this ring is entering, the field is not changing in a proper way. It is messed up. So there is no guarantee field will be radial. So field will be at some random angle. We know there will be a field, but we don't know which direction. You can resolve this into two components, E tangential and E radial. So here, if you look at this, the DL bar also will be parallel here. So integral dot E dot DL will be d phi by dt. So this will be E cos theta DL is d phi by dt. Let this angle be theta. So this will be basically E tangential DL is d phi by dt. I don't know E tangential. No. Let the charge density be lambda. So on this ring, take a small piece here, DL. And on the small piece DL, we are taking E tangential. So torque on this small piece DL will be the force, which is dq into E tangential into radius. So this will be lambda DL E tangential radius. The total torque on the ring will be lambda r integral E tangential DL. Again, I don't know E tangential, I don't know DL, but I know what is E tangential DL. So torque on the ring will be lambda r d phi by dt. So this will be torque into dt will be integral lambda r d phi. D phi is a change in flux and torque dt is nothing but I omega. I of the ring is mr square by 2. Mr square. Lambda r, what is the change in flux? Initially the B is 0. When it completely enters inside, the flux will become B into pi r square. From here we will get omega is equal to, we want to find lambda charge, right? So r square goes off. M omega lambda B pi r. Multiply with 2 on both the sides. M omega. Omega, so I know already V naught by root 2r, multiply with 2 here, that will become lambda 2 pi r. Into B. That's your charge. I messed up a 2 somewhere, I guess. There. B is your answer. Clear with this. The charge Q on the ring will be lambda into 2 pi r. Clear with this? Complex, but you can see how we manipulated that whole equation. You cannot find E, you cannot find that E cos theta and all that stuff. But that entire E dot dl ka term goes off and becomes d phi by dt. That is what saved the whole thing. Any doubts on this page? Any step that you're not convinced? All clear with this? Let's see one more. Let's get this. You have a magnetic field region changing at a rate of 4 Tesla per second. You kept a rod PQ of length root 3 by 2 as shown in the region. Find the induced EMF across the rod, and if the two ends of the rod are not joined by a conducting wire, find the force on the rod. Advanced paragraph question. How do we approach this? So we got this ring. This is O. You gave some rod something like this. This is perpendicular, that is perpendicular. So from here, so we have drawn like this. Now listen to my idea here. So this was P and this was Q. Great. This angle was 60. So let this points be A here and B here. So can I say like this? If I just shade this thing, there is only magnetic field in this thing. So flux only changes here. Outside, so there is no magnetic field. So d phi by dt in the loop, which is O, P, A, B, O, in that loop, or actually you can take the full loop, anyway outside the field is 0, is EMF in the loop. So here it's the flux in the loop is nothing but the magnetic field into area of O, P, A, B, O. You agree? So that area, I can figure it out. I'll find out that area. Great. But this will give you, remember, flux in the loop. But there's one more thing here. Now we know when you have a cylindrical field region, the electric fields will be concentric circles. E bar is a long circumference. Now, if you look at this rod here, suppose if there is a rod from O to P, and if there's a rod from O to Q passing through the center, you will notice the field is always perpendicular to the rod, isn't it? For OP and OQ, the field is perpendicular to the DL. And if E is perpendicular to the DL, there'll be no EMF. So E is perpendicular to DL for any rod passing through the center. Therefore, potential difference in OP, potential difference in OQ must be 0. Is that making sense? So where am I going with this? Now, actually we are done, right? So this entire loop ka EMF I know from the rate of change of flux. And in that entire loop we proved OP mein there is no EMF and OQ mein there is no EMF. That means whatever EMF that I get from here must be in only in PQ. Is that making sense? So Faraday's law gives you the EMF in a loop. Induced electric field tells you E is perpendicular to DL, so OP and OQ will not have any EMF. Then where is all this EMF present? It must be present in PQ rod. Now, can you find that area of that OPAQ? OPABO? Any doubts on this page? So in cylindrical magnetic field regions, electric fields are concentric circles. If you put a rod passing through the center, the rod will be normal. Electric field becomes perpendicular to the length. There will be no potential difference along the rod. And from Faraday's law, EMF in a loop is rate of change of flux in the loop. So in our loop, OP and OQ are useless. So that means the entire EMF is in PQ. Can you find the area of that green shaded area? Physics, max everyone, little geometry, get it? This angle is 60 degrees. Something else is also given. No? PQ is given √3/2r. And 60 is √3/2 r by OP. OP is r by √2. So from here, if I join this line here, this will be radius r. This is point A. That becomes a triangle. And this becomes a sector. This is 15 degrees. So this area will be half into base into height. That will be half r√2. That is a rectangle. Plus that sector will be 15 by 180 degrees. R square by 2. This will be r square by 4 plus r square by 30. You can convert into angles. Theta r square by 2. Sorry, theta by 180. Theta will be how much? Pi by 12. There, that's your area. Then you'll be getting something like that 1/6 and all. So this will be the potential difference. EMF आ जाएगा यहाँ से. Once you get this, the EMF will be B into, and dB by dt is 4 Tesla per second. Current I will be E by R. Want the force on the rod? Force on the rod will be simply what? Current I into length A to P. You should take only AP length cross B bar because there is no magnetic field after AP. And AP length is R by √2. You know everything. Clear with this? So the main thing is figuring it out, how to get the EMF only in that PQ rod. So this is the main catch. Since E is perpendicular to the length, there'll be no potential difference across the rods, the OP rod and OQ rod. Whatever potential difference you get only in PQ. Once after that, it's all geometry. All clear with the shapes. Got this? Next one. So definitely try to do all these problems which we have done today. Pretty good ones. This one, this one, this one, disk. Yeah, that's a little about the induced electric field, but again, the story is still not complete. Now, if you observe something here, do you guys remember what's the conservative electric field? Conservative field. A conservative force is something where the work done by the is independent of the path. So if you look at the induced electric field here, is non-conservative in nature. So consider we have a charged particle here, Q, and we have a circular electric field. So if you look at the work done, it's a radial force, which tangential force EQ into 2 pi r. This is not zero. That means this force is not conservative. A conservative force will be, work done will be zero in a closed loop. But we know potential is defined only for conservative fields. Gravitational force, gravitational potential, electrostatic potential, electrostatic field. So then the E which we are studying, who is this guy then? So basically it has this is an evil twin. So in this formula which you are writing, E dot dl is equal to this d phi by dt which you are writing. This E is not this field, this E is someone else. And this is not an induced electric field. So what's happening exactly? Again, let's go back here. So let's say now you have a magnetic field, you got a this non-conservative electric field. Now see, this thing doesn't care whether there is a loop, no loop, and all, the field is there. Now in this field, if you put a metal conductor, I'm taking circular for more convenience. Now when you put a circular thing, now what happens? This electric field which is present will start dragging the electrons. I'll write this thing as E non-conservative. This force will be this way. So these electrons will start piling up here. And this side will become positive. So you have created in static charges. These are the accumulated charges. These accumulated charges will create a counter field. This is conservative field. Getting it, the field created by this this accumulated charges, which is a static charge, this will create the potential difference. Luckily, why it worked out for us so far, because in steady state, both of them are equal. It didn't matter. We are getting the same magnitude. But technically, it is what E we are using is not the induced field directly. It is something else. So in steady state, the non-conservative field is equal to E conservative. So we don't have a problem using that. It works out. But it could be a theoretical question. In the formula integral E dot dl is equal to this, what is this E? That E is not the induced electric field. It is something else. So now we have everything ready. What is the whole story then? So this is the whole story. See, let's say if you have a time varying magnetic field. This will create a non-conservative electric field. This will not create any potential or anything. This will not do anything. But now if you go and bring a conductor, so if you want to see potential, you need to put a conductor. Now if you go and keep a conductor, then you get induced charges. It's like, there's a wind blowing. Unless you put some balloon or something which gets deflected, you don't know there is a wind blowing, but wind is there. These induced charges will create an electrostatic field. Electrostatic field is conservative in nature. This creates potential difference. And there's no guarantee you will see current. It should be a closed loop. If this was a closed loop, now you get a current. Now what Faraday saw in the experiment, he saw a time varying magnetic field, he saw the current. Isn't it? He really didn't know what was happening, the whole story in the middle. So there, this would be the whole thing. So there are actually two different electric fields we are talking about. One is a non-conservative, one is an electrostatic. Luckily, it worked out for us because both the magnitudes will be equal in steady state. And yeah, so yeah, a non-conservative electric field is your evil twin, who looks same, but this guy cannot actually create a potential difference. Clear with this?
So,
Vihan.
sir, one doubt, like at the beginning, that we basically get an induced electric field because of changing magnetic field,
Yeah,
but magnetic field doesn't do any work.
it doesn't do any work.
So then how is it that it is inducing an electric field that does work?
Who is doing work? Electric field is doing work. This is electric field ka work, non-conservative electric field. Where is
But sir,
magnetic
it was,
field here?
so, but it was created by the magnetic field.
So what is the problem? So magnetic force is doing work. What is the problem?
No,
If it is
sir,
created, then fine. So magnetic force didn't do the work.
okay.
So if I take a book and throw it on you and it hits you, who is hitting you? The book. It is not me. It was never me.
Yes, sir.
Did I say work done by magnetic force is zero? No, no, it is an electric field that was created by magnetic field. So fine, fair enough. You should have actually asked a better question. Why are you getting electric field because of time varying magnetic field? That would be a better question. And the answer would be we don't know. That's the easiest to answer. Unfortunately, that is a problem.
Okay, sir.
Clear with this. So there is much more, there are more confusing things to ask. All clear with this? No. Eddy current. It's like if you use the movie logic now, villain ka son is the hero. Villain doesn't do any good things, but his son will do some things. So what is this? Eddy current. There's a little bit of a theory. So if you take a conductor and you place it in a magnetic field, remember I showed you a video. There was a solenoid kind of thing. You kept a magnet there, it became red hot. If you think about it now, Vihan, magnetic force doesn't do work, but torque due to magnetic force does work.
Okay, sir. Like that.
Also, the torque is also created by magnetic force only. And if you remember, we even defined potential energy for a loop, mu dot B.
Yes, sir.
Forces don't do work, torques will do work.
Yes.
So what happens here when you keep a conductor in a time varying magnetic field, right? So this will start generating current loops, because if the conductor is impure, it will have resistance also. And if you have current loops, I square R, it starts producing heat. It can raise to temperature pretty high. Did you guys ever use an induction stove? It looks like this thing, like a brick. You have a round thing here. You put your pan or something here and the water starts boiling. So same thing happens here. So at the bottom of this, there is a magnetic field which is changing here that heats up the bottom of the pan. If you put a copper vessel, it doesn't work. It should be a magnetic substance. So that's why in induction stove vessels will be separate. You can't use your regular vessels if you've ever used one. Or did you ever use your mobile phone charging? When you put it on some pad, right? It starts charging automatically. You must have seen that wireless charging, right? So same thing happens at the back of the phone. There's a coil there, and when you put it on top of something, it is actually generating magnetic field that induces current in here, and that actually charges your mobile. That is the whole concept of wireless charging. Your induction stove, everything is based on this only. Without a wire, how do you charge then? You're just sending magnetic field, and at that point, you're creating voltage or whatever and generating. Think about it. In the future, let's say if humans have occupied the moon, right? Moon is one of the best place to put solar panels. There is no wind, there is no storm, right? There are no pigeons to shit on the panels, so panels will be pretty clear. Getting it? No, pigeon ka shit is a big problem, right? Pigeon ka shit is acidic. When it goes and falls on a solar panel, it gets short circuits the circuit and the whole panel goes off. And all these panels are connected in series, right? So if one panel goes off, that entire strip goes off. So they create a lot of inefficiencies. So moon we don't have pigeons. That's the biggest advantage you have. Now the problem is not that. So we'll go to the moon, we'll establish a base, we'll put a lot of solar panels, there's a lot of space. But how do you transmit that power from moon to earth? That is a problem. You can't put a wire. So you have to generate them into some high frequency signals and then send them to the earth, and you have to catch them. That is a tech we need to figure out. And the heat produced is called eddy heat losses. So currently, right, we also use this thing in steel plants where they melt up this steel and everything using these eddy currents. Pretty efficient. There are no moving parts, nothing. Easy to control the temperature. You can have a pretty precise temperature. You know, before 1930s, India is the only country to produce zinc. No other country in the world was able to produce zinc. You want zinc, you have to come to India. Because zinc has a problem. Its melting point is, I think, is around 297 degrees. It melts at 297 and it vaporizes at 300 degrees. So in a gap of 3 degrees, it will suddenly become a vapor. So it's very difficult to extract it as a metal form. Nowadays, you can actually control the temperature at 298 and you can extract it. But before 1930s, we didn't have something like that. Then how did Indians extract it? What do you think they did? I call it the biryani method. You ever seen, in marriages when they cook biryani or something? Next time observe this. When they're cooking in marriages for large crowds, when they cook biryani or rice or something, generally biryani, okay? What they do, you have this big thing. Now this thing has a lot of food and everything. You put a fire here and you burn, but problem ye hai, the lower part gets cooked. The upper part will still raw. So what they do, they keep a plate here. They take this chapati ka dough, they seal this, and then they put burning coal on the top. Do you ever observe this? If you ever order biryani by kilo, you'll get a pot like this. They will seal the top part with a chapati ka dough. So you're sending heat from the top, you're sending heat from the bottom. So you're cooking from both the sides. So what these people did in metallurgy, they used to take this entire zinc ore. It is filled with tin and everything. They have small holes at the bottom. Instead of heating from the bottom, they used to heat it from the top. The moment you hit 297 degrees, the zinc, it starts melting. Even before it becomes vapor, it starts dropping down as droplets. You don't heat it from the bottom, you heat it from the top. So you can extract zinc separately, even though you can't maintain the temperature. Every time zinc tries to vaporize, the temperature fluctuates, it starts falling down. So that is how they extracted it. So kind of like that. So this is what happens. So if you take a solid conductor and put it there, it produces all weird currents. So current loops will be formed randomly and you actually lose a lot of energy. So your every electric motor, right? Your fan, AC, everything that you have, they have eddy currents. Did you ever do one thing? When you switch on your fan, switch on the fan for 10-15 minutes, stop it and go and touch the bottom part. It's hot. Observe kiya kabhi? So that heat doesn't come only from I square R, it also comes from eddy currents. So you actually lose a lot of energy in electric motors and everything because of this eddy currents. So they do get heated up. So we can't eliminate them, right? So what we do, we can reduce them by making it into, with insulated sheets. I'll show you how. So if you want to make a cube, don't make it with one single block. If you ever get a chance to break some motor or something, you must have noticed something like this. This is how they'll make it. If you want to make a block, you don't make a single block. You make thin, sheets which are laminated, plastic say, and then you stamp them together to create a block. The advantage of this, the current, right, you still get, but this time it reduces a lot. You can see it becomes localized. Each plate will have its own eddy current. So the overall eddy current decreases. So yeah, you can increase the efficiency. Clear with this? So that's a little about eddy current, not much, just a little theory there. Next thing is self-inductance. Just like we had a resistor and capacitor, this is our third element. Actually, the fourth element after battery. Self-inductance. So what is the self-inductance? Opposition to the change in flux in a system created by itself. This property is called self-induction. What do you mean by that? It is like your right hand and left hand are fighting each other. You oppose the change in yourself. How does that work? Let me take an example. Let's say you have a solenoid. Now a solenoid will have multiple turns. So all these turns together is one system. But every turn has its own individuality. So if you take each turn separately, so if I treat this as coil 1, coil 2, and so on. So when the current is flowing, so this coil 1 will start generating magnetic field. So this coil 1 ka magnetic field will enter the other coils. Now the other coils are not happy about it. They will feel like, this coil 1 is pushing its magnetic field into us and it is messing up my flux. Similarly, the coil 2 ka magnetic field will affect the other coils and so on. You're getting it. Each coil ka field will affect the other coils. Even though all the coils belong to the same thing, they're fighting with each other. Making sense? So this is what I mean by that. So the field due to the first coil gets opposed by the remaining coils, and similarly with other ones. So the B bar due to coil 1 enters the remaining coils, which opposes the change in flux. And similar things happen with the other coils. So basically one part of your system is fighting with another part of the system, even though everything belongs to the same thing. Just like in India, right? Even though we're all in the same country, every state fights with every other state. Just like that. We are bored, so kuch karna hai, so we'll fight on some random reasons. I think that's a pretty normal thing. We humans have a tendency. We can't keep quiet. We are a very violent species. That's what I understood over a span. For example, see, tomorrow, if you make the entire world, right, all belong to the same religion, right, all belong to the same country, everything same, right, everything same. We will still find a way to fight among ourselves. Like, is McDonald's ka burger better or Burger King better? People will find always a damn reason to fight. They will figure out something to fight because we can't keep quiet. That is there in our species only. So when you read history, you will realize that. Right. So this flux, right, is proportional to the current. So more current you send, you get more flux you get. The proportionality constant is given by Li. This L is called self-inductance. So what is the physical significance of this? So higher the L, more opposition to the change in flux. So system with a bigger L value will oppose the flux much strongly than the other one. More opposition to the change in flux. It's like inertia, electrical inertia basically. It's the inertia to flux. There, this is our first formula in self-inductance. Flux is equal to Li. So if you have any random system and if you send a current I, the flux will be Li. That L will depend on the geometrical dimensions. Just like remember capacitance Q is equal to Cv. More charge you keep, more voltage you get. The proportionality constant C depends on the geometrical dimensions and all that stuff. Clear with this? So now we know flux is equal to Li. Then from Faraday's law, we know EMF is equal to minus d phi by dt. So when you differentiate this, product rule minus L di by dt minus I dl by dt. This is the actual formula. Most people, they don't do this. So be careful here. If L is constant, just like F is equal to ma, that is valid only when mass is constant. If L is constant, then your E becomes minus L di by dt. This is called as back EMF. So be careful. E is equal to minus L di by dt is valid only when the self-inductance is constant. If L also changes, then you can't use this L di by dt. Something similar to F is equal to ma. So this is the symbol for inductance, basically a solenoid. And the units are Henry. So if you look at this function here, the minus sign tells you opposition to the change. Again, remember, I don't have a problem with current. I have a problem with change in current. So what do you mean by this? So if you have an inductor and let's say current I is going like this, case one, if current increases, I will try to oppose you. How do I do that? I will put a battery opposite to your current flow. If I decreases, I will support you, just like Lenz's law. So I will put a battery in the direction of the current. So if nothing is mentioned, always assume I is increasing, the sign will take care of it. That's why we call it back EMF. It always puts opposite to the current, the signs will take care of it. Is this clear, everyone? There, that is your second formula there. First one is flux is equal to Li. Second is E is minus d phi by dt, so you get minus L di by dt. So just like in capacitors, we have a parallel plate capacitor. That is our most standard shape. In inductors, the most common shape is solenoid. You can have other shapes also, but so if you have a solenoid of length L, radius R, L much greater than R. L is the number of turns per unit length. Flux in one coil is B is equal to B into pi R square, where B is equal to mu naught Ni. So flux in the whole solenoid will be the total number of turns, which is N into L into the flux in each coil. This turns out to be mu naught N square pi R square L into current I. This is the flux in the solenoid. But we know flux is nothing but Li. I will cancel. We get L is equal to, should definitely mug up this. This is a direct CET level question. Matlab, they'll ask you what is a solenoid and you just put the formula. Also there in boards. If you're lucky, it could be asked in mains also. Recently, they have been doing such things. Straightforward formulas, they do ask. Out of 25, you'll find maybe 2 to 3 questions of that sort. What if, just like you're putting a dielectric slab, you can also put a rod or something inside. What if you put a metallic rod and you have a solenoid around it? Then your self-inductance becomes mu medium n square pi r square L, where mu medium is given by mu relative into mu naught. This is called relative permeability, just like your dielectric constant. And for example, if you take mu ion, it's 4000. The meaning of that is it is 4000 times more easy for magnetic field to pass through an ion slab compared to a vacuum. So there are field lines going, and if you put a magnetic, conductor, metallic slab, ion slab, the field lines will just pass through that. It is a region of least resistance. Clear with this? This is your third formula, everyone. Self-inductance of a solenoid. First one is flux is equal to Li. Second is back EMF. Third is this. Now, if you have a current, you have everything. There should be an energy also. Energy in an inductor. So if your current I is flowing like this, you can treat this like a battery. So what is power? Voltage into current. Which will be L di I by dt. But what is power into time? Energy. So therefore, the energy stored in an inductor is half Li square, just like half CV square. But this thing also tells you something. If the moment the current stops flowing, the energy goes off. So unlike a capacitor, you can't just charge it and keep it aside. You have to put it in a circuit where the current is continuously flowing. That's your energy stored. So how is this energy stored? The same way in capacitor, how is the energy stored? Energy stored in the form of electric field lines. So in a solenoid, the energy is stored in the form of magnetic field lines. So the energy is half Li square. This will be half mu naught n square pi r square L I square. You can arrange this a bit. 1 by 2 mu naught, this will become mu naught Ni whole square pi r square L. That becomes your magnetic field. This becomes your volume. Then we get energy density. Magnetic energy density. I think I taught you this thing in the field pressure. Just like you have electric energy density, you also have magnetic energy density. So basically all kind of field lines are some kind of energy basically. Magnetic energy density is nothing but energy per unit volume. Which is given by 1 by 2 mu naught B square. This is your fifth formula. So energy is stored in the form of magnetic field lines. Yeah, that's a bit of theory about the solenoids. So make sure to go through the notes. We have done almost like 20 problems, but I think last 4 or 5 problems are pretty solid ones. So definitely go through this. Next class, when we catch up, what we are going to do something called, we are going to see inductors. We are going to combine inductors with resistances, LR circuits. So do revise your RC circuits once. Whatever techniques that we use there, everything will work. Remember the general solution, A plus B, e power minus t beta, all that stuff. So everything that you studied, we are going to do that again. So do revise that. Then we'll see what happens if you keep an inductor and a capacitor. So we're going to see LR, LC, and all that stuff. So that part will be kind of similar to what you have done in RC. So that will go a little fast only. So what we have done so far is the main thing, especially the induced electric field and the motional EMF and all that stuff. Okay, so that is there. In case you're solving, I think you should start solving. If you're doing HCV or your booklet or something, you can HCV, so you can do first 40, 45 questions. So start doing it, don't delay it, because the rest of the part will go a little faster and it is not that different than what you did in RC. It looks quite similar. So do start solving. Mostly, I think we should wrap up this in another 2.5 classes. So it will take next week that we will wrap it up. Okay, with that, we'll wrap up for the